All right, I just want to take a little time to go over chapter 2.2. Basically, it's just a kind of brief intro to atoms. We consider atoms to be kind of like a functional unit of an element. They're the smallest thing that you can find of an element that is still that element and has all of the properties of that element. Those are things like density, flammability, reactivity, among other things. And within an atom, there are parts. There's kind of like areas to an atom, the nucleus and the electron cloud, and then there's individual parts and pieces that go into that, which are the particles. So we have neutrons, which don't have a charge, they're neutral. We have protons, which are positive, and electrons, which are negative. The protons and the neutrons have the mass, which you may remember from the activity, and electrons don't really have much mass. You find the protons and the neutrons in the nucleus, and then the electrons are kind of on the outside. Here's an artist's conception of what like an atom could look like, where you've got the nucleus in the middle. Here you can see there's two positives, so those are two protons. We're not really putting any charge on that. That's the neutrons. And then you got this hazy part around it, and that's the electron cloud. So there's one way you can draw it, and then here's another way where you're showing the actual electrons in a discrete kind of energy level. Like all models, there are limitations to this, and one is the space. Like the distance between the nucleus and the electron cloud is quite immense. So if you're going to have a nucleus, the electron cloud would, like this size, let's say the electron cloud's probably going to start, at probably at least 1,000 feet away, at least, maybe further. So atoms of elements have different numbers of, first of all, protons. So the protons, say like hydrogen has an atomic number of 1, has 1 proton always. Well, helium has an atomic number of 2, and that means it has 2 protons. All right, they can't be the same. So the atomic number of an element is different for each different type of element. You'll never see two different elements have the same atomic number, and that's always going to represent the protons. Mass number is the protons and neutrons. We have something on the periodic table called atomic mass, and that is actually an average of all the different isotopes. And a lot of times we just kind of round the atomic mass to a whole number and call it a mass number. So isotopes are going to be 2 different atoms of the same element that have different mass, all right? And the way in which they have different mass is they have different numbers of neutrons. Some are stable, and they may not be as interesting as the radioactive ones. The radioactive ones will spontaneously give off energy, possibly, and particles. Those particles could be something like a big, what we call an alpha particle, which is like 2 protons and 2 neutrons. They could kick out a neutron, could kick out an electron, like a high energy electron, then among other things. We can use those isotopes for a number of different things. For instance, tritium, which is hydrogen-3, glows in the dark. That has different uses. But they can also be used in medicine as like tracers. You can ingest something or what have you, and then you can see it on imagery. So here, I think they would have probably used radioactive iodine to identify cancerous throat tissue in this individual on a PET scan. You can also use it to determine the date of really old things. We actually use carbon dating to determine the date of like organic material. They use the difference in uranium isotopes to estimate the age of the universe and so on. So electrons, you find them in different places within the electron cloud. We call them those energy shells or energy levels. I think levels is probably a better way to term it. If you're close to the nucleus, you have less energy. If you're further away, you have more energy. And you can heat atoms up, and the electrons in the lower energy levels will jump up to the higher energy levels. But when they come back, they actually lose that energy in the form of light. We utilize this as humans in fireworks, where if you put different metals and different substances in fireworks, they will when they explode, they give off different colors of light. And depending on kind of the way the electrons are distributed within an atom will tell us whether or not, or it'll tell us about the chemical kind of reactivity and chemical properties of that atom and or element. Here you can kind of see the distribution of electrons on the periodic table. We have another video that kind of explains how to distribute them. Or if you were to give like a different amount of electrons, how they would be distributed throughout that atom. We have a guest. We have a guest star here. Yes, that's nice. So you can see within the periodic table. Let me back it up. So within a periodic table, this is an abbreviated one. Everything that's on top of each other has kind of the same like outermost electron. So hydrogen has one kind of electron on the outside. Lithium has one. Sodium has one. You go to beryllium. Beryllium has two. Magnesium has two. If you went to calcium, it would also have two. Boron has three, and so on. With the exception of, you got helium here. It has two electrons on the outside. Neon and argon have 8. And there's reasons for that, which we won't go into now. And that's it for chapter 2.2.